Hello everyone. So in this whole course we have looked at a lot of theoretical aspects of indoor air quality, particulate matter, physico-chemical contaminants. So particulate matter, volatile organic compounds, different gases. Then we have looked at also the biological bioaerosols. We have looked at the methods of their detection, and also we have done calculations for assessing their burdens in the indoor air quality in any area, and also the risk assessment associated with that. Now if we have one or two chemicals, we can probably do the calculations by hand. If we have one or two rooms, we can do the calculations by hand. But if there is a situation where it is a normal building or a normal house, we know that there are many contaminants in that house. Many contaminants, many bioaerosols. Also, it is often not just one window. There may be a window, there may be an exhaust fan, there will be a door, a balcony door, and they may open and close at different amounts of time. Then even when we have different sources, cooking is only for some time and then not for some time. Humans emit CO2, but we may not be occupying the indoor environment for all the time. Maybe 12 hours we will be at home and 12 hours we will be outside home. Then some people will come in for 1 hour, go out, then come in, then go out. So then the whole pattern, the level becomes so detailed that it is more difficult to do these calculations by hand. Either difficult or it will be very time consuming. And then suppose we are able to even accomplish that, how will we then there are different options. Let us say some chemicals concentrations are higher than the guideline values or higher than what we wanted them to be. So then we want to evaluate different options to reduce the concentrations. Those options could be installation of particle filter or installation of gas filter, or somehow reduction of source, or increasing of ventilation rate. So of course we cannot do all these experimentally, because we cannot bring the filters and put them in the inlet and then wait to see how the improvement are, because then what if it's not good, then we have to buy another filter and do the whole thing again. So it is very cost and time ineffective. Likewise, we cannot keep on manipulating the air exchange rate and see experimentally. So let us say we want to do these calculations by hand. So if we do these calculations by hand, again for every intervention or every possible intervention, we will have to do the whole sequence of calculations again, and then check, is this intervention going to give me an improvement or is it not going to give me an improvement. Then we have so many different elements and transports from one room to another and from outside air to another, and then we have options, mechanical ventilation or just diffused transport of air. We may have ducts, we may have recirculation, and if we want to understand in a present building how that is leading to poor air quality, or if you want to design a new building and check, okay, how do we improve the air quality, then it is very difficult and time consuming to do all these calculations by hand. So a simplification in terms of the effort is made when we have a computer based model, because then if we can set up the model appropriately, we can do all these interventions by means of a thought process and by means of the parameters of the model, and then we can check if these new interventions as expressed in the model will give us the desired result. And when we get those desired results, we can go and design our building accordingly. So in this lecture, we are going to look at the introduction of one such model, which is free and also quite widely used. and that model is this Contam. So Contam is a computer based indoor air quality modeling tool, and it is used, and its purpose is to predict and analyze in buildings the indoor air quality. So indoor air quality with respect to CO, CO2, PM 2.5, PM 10, PM 1, all the gases, formaldehyde, acetaldehyde, even heavy metals it can do. So all the contaminants that are possible in an indoor air quality, we can in principle include them in this air quality model. We can also analyze the air flows, that how much is the flow going in and out, how can we modify those airflows to improve better the quality of the indoor air. And then the contaminant transport. So how is the contaminant being transported from outside to inside, from inside one room to another, or is being exchanged between different rooms, and then how it leaves the building also. So the whole flow path, the whole transport pattern of the contaminant can be assessed by using this model. And once we start looking into this model, we will find that it has a lot of capabilities. Even emissions, one can have different types of source, a constant source or an exponential source, a decaying source. Anything is, almost all the possibilities have been accounted for, or it is possible to express all these possibilities into the modeling framework of the Contam. So it has very many capabilities. Of course, it is teaching the Contam itself. Contam in itself is 1 or 2 courses. So that we are not going to, in this lecture, we are not going to learn the all ins and outs of the model. The purpose here is to give an introduction, to give a frame, to show Contam what it is, how it can work, and maybe then maybe the student can take it up for more in-depth learning or application, and it is quite easy to find a lot of tutorials and also user guide, and even the Contam itself will give all the theoretical Contam documentation, will give you all the theoretical information and all the sort of information on how to set up and run the model. Otherwise, you can find this in various online sources. So it is a very exhaustive model, has many capabilities, and also it is basically free to download and use. You can use this model quite easily. The model was made at the US National Institute of Standards and Technology. And then so it was made there, and it is basically publicly available now. It can be used for quantitative analysis of indoor air. And so what is the quality, what is the quantity? It can be used to analyze different optimization strategies of ventilation. This is filters, spelling mistake. So it can be used for a lot of quantitative analysis, optimizing the ventilation strategies, that how can I modify my flow rates so that I achieve acceptable air quality. And we will do this, we will look at it in the in this course as well, very briefly. We can assess the effects of installation of filters also. Which filter is going to give me the quality that I want. We can also assess the effect of installation of filters. We can use this at the designing phase itself, the location of ventilation, the location of ducts, the quality control we want to apply in those inlets and outlets, and many more. So the program itself has a lot of possibilities. For example, in Air Force, it can model infiltration. So infiltration of air from outside to inside. Then also exfiltration, which is the movement of air from inside to outside. So infiltration and exfiltration both can be modeled. It can also model room to room airflows by mechanical means through differences in the pressure between the ambient air and the room air. So the effects of this pressure. Also the buoyancy effects, in the sense the temperature in the outdoors and indoors, when they are different, there may be buoyancy effects, so air lifting, and then the movement of air taking place because of these differences. So in principle, Contam is now able to model all of these airflow patterns. Then the next is the sources. So it can the goal is to get the concentrations of different pollutants. So the model is able to signify, you can add the sources in this model of different contaminants. You can also model sort of the dispersal of this contaminant using the transports and flows that were in the previous slides. It is also possible to include contaminant transformations by reactions. It is possible to model the adsorption and desorption to building materials by suitably choosing the parameters. One can include filtration as well, filtration of incoming air, or if one is trying to recirculate the air, then it could be, one can filter the recirculating air. We can also model the deposition to the building surfaces. Then it is possible to also make some kind of exposure analysis, so that may help us in the eventual risk assessment, which is also one goal of having an indoor air quality guideline or air quality guideline for sort of no or low risk. And when we have the data from this Contam, it is possible to do that. So now we will look at a simple demo with the suite being modeled and the contaminant being CO2 with one occupant, and here I will show the setup of the model and the plotting of concentrations. So one can just download or obtain this Contam by just doing Google. You can search Contam and just write Contam download, and you will get a hit on the Contam website itself, and you can download and install Contam in your computers. So we will look at the demo for Contam now. So once you search the web for something like download Contam, you will get a hit on for the NIST.gov website, and you can arrive at this page called download Contam. So please go ahead and download this Contam model. Right now the version they are saying is 3.4.0.5 April 2024. So this is the latest version. Just download this and go ahead and install it. Once you install, you will have a once you install, you will get a Contam console. So just go Contam and click Contam 0, and this window will open. So this is, let us say, is our workspace. or the um, area where we are going to put our model in. So now that we are at this stage, we have to define what we are working on. So first is the setup of the workspace itself. So we will go to file and go to project description. So here I am going to write the description as demo. So it is like a demonstration. Okay. Then the next thing we have to do is go to view and come down to the here to the project options. So now there are this window will open. So first thing is what units we want to use. So I am going to use SI units. We should it depends on your preference. We can use SI units. And what are the units of flow? kg per second, standard meter cube per second, feet cube per hour. So there are so many options. So I am going to use this meter cube per hour option. Because we are always using it in the flow is in meter cube, so we will use SM cube per hour, because we are talking about the way we have done in this lecture or in this course is flow is by volume per hour, so we will stick to this standard cubic meter per hour. Default zone and junction temperature 20 Celsius, we will let it be, because in our demo at the moment this is not important, we will let it be. Then the sketch pad dimension. So this area is basically called a sketch pad. So place where we can do the sketching and set up our building. So right now this white space is there. I want to expand it to maybe occupy more area, this area. So I am going to add the sketchpad dimensions. I am going to increase. I am going to make it 130. Height, I think it is sufficient for me. I want more width, so I make it 130. So as you see, this white space has increased. So I think this much is enough for us or for me to show this demo. According to your screen and your comfort, you can choose this area as you like. Then we have done view, then we go to level and we go edit level data. So levels are basically levels of the building. So we are basically at level named 1, elevation is 0, so basic, and distance to the level above. So the height, basically height of this level 1 is the distance to the next level. So we are going to use a height of 3 meters, which approximately is just a bit less than 10 feet. So let's say approximately 10 feet, which is pretty much standard. We can have approximately 10 feet ceiling. So 3 meters we will consider the height of this level. So distance to level above is 3 meters. So okay, this is defined. So in case it is not defined, just enter 3 and that's it. You can press replace and this will update this value. And we click, so after entering, just do replace, and then you see level 1, number 1, level name 1, elevation 0, height 3. So okay, done. Then we have to specify the ambient. So our room or our suite is in ambient, like it is situated in the area. We will define the ambient situation. So for that, nothing, we just have to go somewhere, let's say on the left side, and right click, and this options will open. So I'm going to just choose ambient. So now my ambient is set. outdoor is set now. Then we have to choose our our actual um, location, our actual building, which we have to model the indoor air. So now if you see these options, okay, find and replace. This is draw walls. We can draw walls, or we can just draw. So right now we are just going to have a area wise suite. So I'm just going to draw a box. So we select this, then click and drag, then another click. So we have this area there. Now this is what they call is a zone, and zone in our case is that enclosure, and we can name it now. Our suite is basically a zone. So to define this area, we will right click inside, and now we can say this is our zone. So you see like some blinking is happening, and this is highlighted. Now we have to define the characteristics of this zone. So we will go over this area, highlighted area, and double click, left double click. So this window has opened. So zone name, we are going a suite, so we will say suite. The level is 1, fine. The floor area, we will use 40 meters square, which is approximately 430 feet square. So we give the area, it will automatically calculate the volume. Because our level height was 3 meters, if the floor area is 40 meters square, the volume would be 40 multiplied by 3, 120 meter cube. So already this dimensions and the volume of the suite is fixed. Now we will see there is something called as contaminant data right here. If we click here, we don't get anything like contaminants, but this is written no contaminants and everything is blank, because so far we have not defined our contaminant yet. So let us do that. So I am going to click OK. So you see the suite properties have arrived. Suite level 1, temperature constant at 20, volume 120 meter cube, area 40 meters square, and height is 3 meters. Okay, fine. So now let us see how to add the contaminants. So again we will go to this bar and we will go to data. So now we can have airflow elements, duct elements, wind pressure, weak schedules, occupancy schedule. Here we have the contaminant. So let us specify which contaminant we want to model. So this window will open, and again we see that this place is empty and there is no contaminant. So and this is also all blank. So we should now enter a new contaminant. So we will come here and add new, and this another window is going to open. So since we are going to model CO2, let us add CO2 in the name, then molar mass. CO2 molar mass is 44 grams per mole. Here we have to enter in kilograms per kilomole. So 44 grams per mole is basically the same as 44 kilograms per kilomole. So I am going to go back here and write 44. These things need not be changed, and we don't need mean diameter also. We'll come here to this place, default concentration. The default concentration is essentially the ambient concentration. So ambient concentration for CO2 is Let approximately give or take 400 ppm. So we are going to use a default, which is ambient CO2 concentration in ppm and as 400 ppm. Okay, so basically we have added the contaminant here, CO2, then we have put its molar mass, and then we have come down, and the important part is the default concentration. So it is 400 ppm, which is basically the ambient concentration. And we need to simulate, we want to see the evolution of CO2 with time. So we will say use in simulation, yes, check. So okay. Now you see it has been updated, species CO2, contaminants CO2. So let us say okay. So our contaminant is done. So we have defined the contaminant we want to model. Now at the moment, for first instance, let us check the scenario where the indoor air is only influenced by the outdoor air. Eventually we will put an occupant inside who will release CO2. But first, to see if the model results match with how we think it should do, let us try to not put an occupant first. So we have the zone and we have outdoor ambient conditions. Let us assume that initially the zone has no CO2. So we again go back to this zone to define the zone conditions. So this zone box I am going to double click. Again you see, you remember we just put this zone data as suite and floor area 40 meter square. So the volume is 120 meter cube. And this contaminant data bar was here, which was empty first, but now we have CO2 there. So CO2 contaminant is variable CO2, initial concentration of selected contaminant. So we want to start from 0. So the room air was clean, and now only the ambient air is coming in and ambient air is going out, and we will see how the concentration evolves in the indoor air with time. And right now there is no source, so concentration is 0. Now right now our box, our suite, our zone is in isolation. If you see, there is no interaction with the ambient air. So we should add some flow element. So we are going to define some flow elements now. To do that, let us have inflow from the left side, or inflow from this side, and outflow from the other side. So to define the inflows and outflows, we have to add what they call a flow element. So I am going to just single click on this left wall. So again, once again, if we are here somewhere, we will just single click. You see this black spot is there now, and then right click on top of it, and we see these options coming out. So we have, there is a flow path which is highlighted. Let's click this flow path. Now you see there is this blinking is occurring, which means this point has been assigned as a flow path now. Now to define the properties of the flow path, I will double click. Now you see this new window has been opened. So the first thing would be, okay, what does it say? Flow element. Right now everything is empty. Name required. Flow element's name is required. The description is also empty. So let us add this new element. So I clicked. Now we are going to assign a constant flow this time. So there are a lot of options: one-way flow using power law models, one-way flow using quadratic models, two-way flow, one opening and two openings, backdraft damper flow, cubic spline flow models, and here we have fan and forced flow. So these are forced flow in and out of the building. So let us assume there is a fan or some sort of mechanical ventilation whose flow is fixed. So we are going to have a constant flow this time. So constant volume flow. Click OK. So name. Let us define it as a fan which is bringing the air inside. So I will write fan, IN, fan in. Just to name it. Now design maximum flow rate. So our design flow rate, our volume is 120 meter cube. So if we want to design the model for 0.5 air changes per hour, our flow should be 0.5 times 120. So this would be 60 meter cube per hour. This would be our flow rate for achieving 0.5 air changes per hour. So if I click in this units, we want to use meter cube per hour, and this would be 60. So we have mechanical, let's say, ventilation with air changes per hour of let's say 60 by 120 equal to 0.5. So 60 meter cube means 0.5 air changes per hour, right? 60 meter cube per hour is the volume, and 120 meter cube 60 meter per hour is the volume of the air that we want to come in and flush the indoor environment, and 120 meter cube is the volume of our indoor environment. So air changes per hour becomes 60 by 120, 0.5. So okay. So if you see here, this element has been incorporated, fan in, design maximum flow rate 60 meter cube per hour. Now there is this thing called flow path. So flow path, we want the air coming in from outside to inside for this fan or this ventilator. So we will put positive flow direction. Okay, we are going to have the ambient to sweet flow. Then we have things called schedule. Now schedule is essentially going to tell how often or from what time to what time the fan is open, and to what amount, half open, full open or not open. So in our case, let us assume first or in this demo we will assume that the ventilation is always occurring. So we will create the schedule for this fan. So we are going to come here to new schedule. Now I am going to name the schedule as fan in underscore always on. So the incoming fan is always on. So mechanical ventilation description, mechanical ventilation for outside to inside is always on. So what is the schedule? So abhi display, if we do, there is all day schedules must be set prior. So we have to set this available schedule. So we are going to come here and say new day schedule, and my new day schedule is always on. Display graphically. So right now it says at 0000 midnight it is 1, and at 24:00:00 it is always 1, also 1. So let us see it graphically how it looks like. So it is always 1 1 1 1 1. So it is constant, and 1. So it is always on. So we will keep it always on. Yes. So now this schedule is available, and this is the fan schedule. So we have to give this schedule to the schedule of the fan. So I will select always on and select all of them and say replace. So now you see the schedule of all the days is always on, always on, always on, always on. Now it means the fan is always on. This now I'm going to just confirm this by checking display graphically. So you see the schedule is now 1 all the time. So now the fan is basically on always. So this completes the incoming fan description. I will click OK. There is also an option for filter. For this demo, we are not putting filters. We will take it subsequently later. So we have an incoming flow of 60 meter cube per hour, which corresponds to air changes per hour of 0.5. Okay. Now this air is coming in, it has to also go out. So we are going to introduce another flow element, another forced mechanical ventilation to take out the air. So again I am going to left click on this right wall and then right click on this spot and have a flow path. Yes. So now this place is highlighted. I am going to go and double click it. So now we see there is nothing here what this flow element is about. So I am going to create it, clicking new element and constant volume flow, and name I am going to give fan out. What is the design flow rate? So our design flow rate for incoming was 60, outgoing also we will keep 60 meter cube per hour. So I will change it to 60. Description same flow as fan in. So we are trying to maintain, or at least by design, 60 meter cube per hour. The flow path, the positive flow direction we will keep sweep to ambient. So anything that is going in this direction outside to this area outside the box will be the positive flow direction for sweep to ambient. Then schedule. What is the schedule for this fan? We are going to keep it always again on. So schedule, new schedule. So we will say fan out. Now available schedule always on. Always on is always 1.0. It is available. So I am going to copy this available schedule to the fan out schedule. Replace, and then I have, let me just check if we will check if it is correct as we wanted it to be, and we see it is always 1.0. So this is okay. We will keep this schedule okay. So we have done the flow element description, we have the flow path, and we have the schedule. Filter we are not going to install right now. So we will press OK. Now both of these elements are forced flow elements. So we have to add also sometimes there can be leakages in the building. So we will have a leakage point here, let's say in this edge. So I will click on the line and then add a flow path. Now this is highlighted. I will double click it. So we have a flow element. Let's create a new element, and we are calling for a leakage. So let us go for a leakage area data. Press OK. So name we will give leakage. Let us define it as leakage area per unit area. So for this case we will do a nominal 1 centimeter square leakage per meter square. Things such as discharge coefficient, flow exponent, pressure difference we will not touch. Small opening, okay. Flow path, let us use positive flow path from suit to ambient going up. This is our edge. So if it goes this way, we will take it as positive. Schedule. So what is the schedule for this particular leakage? So let us see, we will create a new schedule for leakage. and we are going to say that this schedule is also always on our, so we have a schedule called always on available. We are going to put this on the whole always on for the leakage schedule. So the leakage is always happening. I have copied it. Let us see it graphically. So it is always 1.0. So the leakage is always possible. There is no filter on the leakage. When we have these two forced, when we have this and this as forced fan or forced flow models, we may need this leakage to also close the pressure and flow schemes for the model. So we have our flows defined. Our contaminant data is also defined as 0 ppm, and we have also defined the flows and leakages, and the ambient is 400 ppm. So we have our model zone, which is suite with a defined area, a defined volume, and the designed flow rates coming in and going out, and we have the ambient concentration of CO2 in ppm. Our goal was to see how the CO2 will change when there is an occupant, and the occupant goes maybe in and out, but we will see. Right now, first our goal is to see how the concentration evolves inside if it is only influenced by the outside concentration. So we have outside ppm already there, the flow rates are defined. We are ready to do the first simulation. So to do the simulation, we will come to this option called simulation, click and go for set simulation parameters. So we will have first thing called run control. So we will use simulation method as transient, so things will change. Now we have contaminants we also want to have transient, so that they are calculated real time, transient. Then integration method, we will leave them as they are, leave these as default whatever they are. For transient simulation start, it starts at January 100. Let us do a 1 week run. So we will choose this as end stop, the transient simulation stop at 7th of January as soon as the time becomes 24:00:00. So the simulation will start at 1st January 00:00:00 and the simulation will end at January 7, 24:00:00. Then let's check what is in the weather. We have steady state weather data, transient weather data none, use steady state weather with OK. Transient contaminant data no, use steady state. So let us use just single value for now. Then output, airflow rates detailed. Then we have contaminant concentration detailed. So let's keep this. Let it save a summary file. Then surface file, log file. Let us leave it as they are. Everything also we will leave as they are. So our simulation parameters are now fixed, and we are ready to do the first simulation. So I am going to click on simulation and do run simulation. Since it's a new project, it's going to ask what is the project file name. I will just check demo and save. Okay, there was another demo. Okay, I will replace it. So our demo project is now ready to run. Now there is something called simulation control. It's telling us the situations that it will do, the settings. Airflow simulation transient, okay. Contaminant simulation transient, okay. Simulation date 01 Jan to 07 Jan, okay. Start simulation, close. So first thing what we can check is what is the flow rate. So let's just hover our mouse over this point and click. So it is 60 meter cube per hour as we designed it to be, and outflow also is 60 meter cube per hour as we designed it to be. The zone volume was 120 meter cube. So our air change is 60 by 120, so 0.5 per hour. There is no flow through this leakage. Everything is going forced in and out. So the model is basically exactly as our one box models that we did earlier in the course. Now what we were interested in is the evolution of CO2 with time. Now you recall that there was no internal source of CO2 in this model as yet. The values are only driven by the outside ambient concentration, and we started from zero concentration in the zone. So if we start from zero concentration and the only source is outside, we will expect the concentration to increase from 0 to ambient air concentrations and then remain at the ambient air concentration as the box keeps on flushing with the outside air. So outside air is coming, replacing the inside air. Air is coming, replacing the inside air. So in the steady state, the indoor air concentration should be equal to the outdoor air concentration. So let us see if that happens or not. We started with 400 ppm in the outside and 0 ppm in the inside. So now we can just right click anywhere inside the box and do plot contaminants. Then this window will open, which basically is saying, okay, single contaminant, CO2, units ppm, okay, zones to plot, zone 1, level 1, sweet, okay, dates to plot, results available from January 07 to results available from January 01 to January 07, plot the results from January 01 to January 01. So we want to plot from January 01 to January 07. So we will change this, plot results from January 01 to January 07, and we will click plot data. So you can see easily that, so on the x-axis we have time of day. So first day 0, 12, then second day 0, 12, then 24 is somewhere here, over 7 days. And as expected, the concentration, this and the y-axis we have CO2 concentration ppm. So the concentration rises from 0 to 400 very quickly. So because the half of the air is flushed every hour, our air change rate was 0.5 per hour. So we see within 12 hours approximately we have reached the steady state, and the steady state value is the value of the ambient concentration, and then all the time it remains as it is. So the model indeed performs how we think it should perform. So now we will, this was how the indoor air was influenced by only the outdoor source. Now we will do what happens when there is an occupant who is influencing the CO2 inside. So we were going to, first we will close this windows. So we will come here and click done. Now we are back to this figure, and you see there are a lot of flow rates and things are there. We want to go to the original view, so we will go to view and click normal mode. Now we are at here. So when we have a source inside the box, inside our zone, we have to add the source. A human basically is this constant source of CO2 as long as the human is there. So now I am going to right click here and check source sync. Now this point is highlighted. So now again I am going to double click, and it says source sync element. Right now there is nothing there, so we will add a new element, and we are going to use a constant source through the human breathing. So we will choose constant coefficient, click OK. So the name of the source, so name I am going to give occupant CO2. The generation rate of an adult is typically around 0.005 liters per second. So there is no removal. Description I will write CO2 from the occupant. and click OK. The multiplier we do not need to change, we have one occupant. What is the schedule for this occupant? Is this occupant there all the time or not all the time? For first part, we will assume right now that the occupant is always there in the room. So we'll click new schedule and we will name it occup always on. So the occupant is always on. Right now we did not assign anything, so all the schedule must be set. What are the available schedules? We have a always on schedule. If we double click and see display graphically, this is always occupied. So we will go ahead and copy this always on schedule to everything on the occupant always on schedule. So available, we will replace everything. So now the schedule for occupant always on is always on. Display graphically we can check. Everything is 1.0. So the occupant is always there. We will click OK. Our occupant is there. We will click OK. Our flows and zones were already defined. So we are ready to go on. So I am going to go simulation. Let us just check simulation parameters for checking sake. So simulation method transient, contaminant transient, everything is the same. Transient simulation start at 1 January, stop at 7 January. Okay. So now we can just run the simulation. It will give us the simulation settings for confirmation. Everything is the same. Start simulation. It runs very quickly. We can close. Again we have the flows. We have the flow 60 meter cube per hour here, 60 meter cube per hour here. But now we have the extra source. So now in addition to the ambient air, we have an extra source inside. That means when the extra source starts at time 0. So we have time 0 ambient air coming in, plus the person is also giving out CO2. So we will expect the slope to increase sharp, and we would expect the steady state of this slope to be higher than 400 ppm, which was derived when there was no occupant. So we will again do this right click and do plot contaminants, and we have contaminants to plot CO2, okay, zones to plot level 1 suite, okay, date to plot, results available from Jan 1 to Jan 7, okay, plot results from Jan 1 to Jan, we will do Jan 7, and we will go plot data. So again, as expected, again the concentration will rise more to more steep extents. So before we were stabilizing at 400, now we have reached to 700, and around 12 hours we have stabilized to 700 ppm. So on the y-axis we have concentration of CO2 in ppm. So this is 700 ppm time of day. So we have stabilized to 700 ppm, and then it remains at 700 ppm. So the model is still behaving as it is, and probably this can be calculated by hand also. Now the final thing we want to check here is that if the occupant goes in and out of the building. So let us say the occupant goes out at 8 am and then comes back to the suite at 8 pm. In between we will assume that the ventilation and the flow is always going on, but the occupant only occupies the suite from 8 pm to 8 am, that is 12 hours a day. The other 12 hours, 8 am to 8 pm, the occupant is not there. So we will expect some kind of increase decrease because the occupant goes away. So to simulate that, first of course we will close these results. Done. We will go back to view normal mode, and now we have to modify the source properties. So this was our source, always on. So we will double click here So instead of editing this, I'm going to add a new option. So this is CO2 from occupant, always on. I'm going to add a new element. This is also going to be constant, only it will happen 12 hours a day and it will not happen 12 hours a day. So actually the source is still the same. The occupant emits CO2, but the occupant will only be occupying 12 hours a day. So we can modify the schedule of the occupant. So we don't want the always on schedule. Right now everything is always on, always on. We don't want always on. We want to have a 12-hour schedule. So we will do new schedule. So I will write occupant 12 hours. And description, occupant only occupies the suite for 12 hours a day, 8 p.m. to 8 a.m. So this is definitely not our always on schedule. We have to make a new one. So new day schedule, 12 hour. I will say occupant 12 hour. Description, on from 8 p.m. to 8 a.m. otherwise off. So at 0 it is on, it turns off at 8 a.m. So we will go to here, edit schedule value, time 8, select double click, highlight it, 8. The value becomes 0. So I'll make it 0 and insert it here. So let us see how it looks like. Sometimes it will give an error. Let us delete and just do it again. So it closes at 8 o'clock a.m. and it turns on at 8 p.m. So let us make a 20. 8 p.m. is 20 hours and make it 1 again and insert. Let us see how it looks like. So you see it remains 1, so on until 8 a.m. So on the x-axis we have hour of day, y-axis is our opening or closing. So it is open until 8 a.m. At 8 a.m. it closes, then close, comes 20 hours, which is 8 p.m. At 8 p.m. it opens and remains 1. So this is our occupant 12-hour schedule. So let's create this, okay. And our schedule for this occupant is now occupant 12-hour schedule. So I am going to use this schedule for the occupant. So replace for all. So now our occupant schedule is as we want. The person is occupying 12 hours a day. We click OK. Now we see we have several options for schedule. We can choose occupant always on, or we can also choose occupant 12 hours. So this is what we want to try right now. So we are going to choose occupant 12 hours one day. So we'll click OK. So now you see source is occupant CO2. So occupant CO2 emissions at our specified rate, but the schedule is occupant 12 hours. So the occupant is now only 12 hours instead of 24 hours. Everything else we have not changed. Now we are ready to start the simulation. So just as a practice, let us check simulation parameters. In case something changes, we must be able to find it and rectify it. But of course here we see simulation method, airflows, transient, so fine, contaminant, transient, fine, everything else is default. Then we have transient simulation start at January 1, okay, transient simulation stop at January 7, 24 degree. So nothing changed, everything is fine. We will let other bars be wherever they are and we will press OK. So now we are ready to run the simulation. Now the time starts. Now let us see how do we expect it to be. How do we expect the CO2 curve to be? So at time 0, we have 0 initial concentration and air is coming from outside. At time 0, which is at midnight, the occupant is in the room. So there will be a source from inside and the outside both. So we will have some increase until 8 am. At 8 am, the occupant will go away. So the increase will not be as much, and if the occupant source is dominating the outside source, then we may also have some decline. And then at 8 pm the occupant comes back, so we are expecting the concentrations to rise again. So some kind of up and down probably will come. So let us start the simulation. Run simulation. Again we can check everything. It is the same. Start simulation. The simulation is over now. Close. Now let us plot. Plot contaminants. Single contaminant, okay. Units, okay. Zones to plot, level 1, sweet, okay. Date to plot, results from Jan 1 to Jan 7. Plot results from Jan 1 to Jan 7. So we will change this and we will plot. So again, as we were expecting, again we have met the model is what we thought it would show. The model is showing that. So we have the x-axis time of day, first day, second day, third day for 7 days. On y-axis we have CO2 concentration. So the concentration rises quite rapidly but does not go to the final value because the occupant has left the room. So the concentration will try to go down, it goes down. Then the occupant comes back at 8 pm, so the concentration rises again. Then the occupant goes, then the occupant comes back. So it's up, down, up, down, up, down, up, down based on the occupant behavior. So in this demo, we have seen how Contam can be set up and run and be used to run simple simulations also. Of course, there are a lot of options in this Contam model, and according to the requirement of the user can simulate a suite, a house, different rooms of a house by defining adequate flow paths. The scope and the objective of this demo was to show how to set up and run the model for simple scenarios, and in one of the subsequent lectures we will also use this to evaluate some pollution control or indoor air quality mitigation measures, how we can use Contam to assess those simple measures. So with this we will conclude the demo of the Contam, which is a free indoor air quality model.